Um, Good morning, Professor.
Good morning.
Uh,
Your
Good
audio.
morning, everyone. Good morning.
Good morning, Brian.
you're right. Uh,
Jesus, your audio seems a little loud.
okay.
Just, just a bit.
It's better now.
Yes, still loud, but it's better without any distortion.
Maybe, maybe now.
Yeah, it's good.
Okay, thanks. Mm. Oh,
Yes,
Professor Garrett is not going to join with us. Mhm.
yes. I understand from his email that he's occupied with preparing for a meeting on Friday.
Yes, yes. Maybe I am going to go to the meeting. Uh,
Ah,
t- only for the Professor Garrett conference. Only
mhm,
for that. Yeah. Mhm. Mhm.
yes. Well, hopefully we'll hear from him. And if you manage to attend the meeting, then in our next meeting we could discuss uh, the results of that presentation.
Yeah.
Uh, at this point, I still remain a little bit, I should say, maybe skeptical about the notion of duality that Dr. Sobchak is considering. This notion of local duality, I guess, is still to me kind of mysterious idea. But it seems to me somewhat away from the notion of duality. No longer directly related to what would commonly be called duality. Um, it's
Yes, because I don't. Um, I wanted we can start with a formal definition of duality, and then with this we can understand what are we saying about local and global duality.
yes.
Nevertheless, I was trying to um, understand more about the idea. I found some definitions about the Fano plane. Sorry, Fano plane that is where more precise. I found the idea that Professor Garrett is presenting about duality, interchanging dots and arrows.
Ah,
Yes.
yes, yes. Uh, that's interesting. I did do a little bit of background reading about this Fano plane, and um, it sent me in the direction of projective geometry, right? So we're we're talking about uh, something which seems to be a inherently geometric notion, um, which is uh, I'm not uh, I I I guess it's interesting that you have now a way to view this in a more algebraic way, like in a way that emphasizes the algebra as opposed to the geometry.
I was trying to review this from the algebraic viewpoint, but I did not finish yet. But I found the idea of duality there because the algebraic approach is like in the is like the algebraic approach of graphics. Then I think that we can use that algebraic approach of graphics. For example, that and many authors have been working in graphics and formalizing the theory of graphics, introducing algebra of graphs and something like this. But I remember that Knauer and Knauer present one approach to graphics in terms of category theory, like the category of graph. And then it is too much interesting because one can use many or all the concepts of category theory inside the graph theory in the category. And I was trying to understand the Fano graph in this way. But when we try to interchange vertices and arrows, I remember the idea of Professor Rosiewicz with operas. That and there we have an interchange of arrows and vertices.
Oh.
Then I think that we can relate this idea in the of duality in the Fano plane with the idea of going to the commutative diagram to operas.
Yes, that sounds very interesting. Do you have any slides or?
I don't get to prepare. I have many slides of the past ideas, but maybe I can present some graphics that I can draw in my iPad. Only I'm going to connect to the meeting. Then I am going to put off the audio here.
Okay.
Okay, can you listen to me?
Yes, that's just fine.
Okay, thanks. Okay, I'm going to put in my screen the whiteboard, and the idea is that the Fano plane can is a kind of a Cayley graph, and then here we can oh, okay. Okay. Yeah, I have problems with the battery in the pen, but I'm going to use another, not better than this. But the idea is here this graph is of this form. And sorry, I need to check. Okay. Mm-hmm. And
do we have
then
directed edges?
Yes, but not necessary. Not necessary. But we have it's in the okay. It's something like this. It is like a set of relations between this vertex. And then the idea is that we can interchange the dots with the arrows. Those we have. I am going to put names here. B, C, and B, capital C, and A. capital A. Okay, and then we can we have that every is arrows to vertex.
So when you inscribe this circle, you have a circle A B C, capital A B C is a circle, or should I consider this just three edges joining?
Just the three edges that are like the meam of the segments B, for example. Capital A is in half of the segment CB.
But so far, the idea that there is a circle is not necessary.
I don't know if for the definition of course, for the definition of anoplane, it is necessary, but I don't remember now the of this. But I wanted only to speak the idea here, because he speak about duality in one interchange of arrows and dots. And it is possible because with example, with the arrow AB, in this way, we can for example, if we think in the category theory like Homestead, we have AB here. But if we think in only in a vertex, then we can see that these have an input and an output. This is maybe we can put this A and AB. Then the idea that go to relate CA one arrow to AB. And CA are, in this case, dots.
Okay.
Then if we remember from a commutative diagram, for example, we have this object, and if the H, we say that the relation here are in this form. G after H. Sorry, those are arrows in this. And this in this way, the set A can be represented here, and then we have a process F here without and a process H here with an outside. And then this came if G, no, sorry, not yet. After F, I have a process G, and we say that those are those are isomorphic. Then have the objects A, B, and C, A, and C is the output. Then relation in the opera terms that we can interchange this graph with this representing to this equation. And here I am going to raise now the objects that I put here. Okay. Then this is the same exercise that we can make a Fano plane. And but this is not a duality. But because we are representing the same properties in two different ways. Then I don't I understand the term you said in the Fano-Plane articles around duality, but they use the word duality that are not corresponding to the concept of duality that we use in category theory. Because if we want to speak about about the concept of duality, then we need, for example, two categories. Oh, sorry, I am going to start only with one, and then I can say that this category have objects here that I'm going to call with lower letters, etc. And then we can build an opposite. Sorry, I need to put some
So we will interchange the direction of the arrows.
I'm going to add one more. The arrows, yeah. And then in the opposite, the objects are the in such a way that I put here up a up is the same that A. That is objects of objects in A are the same that objects in A up. But the morphemes here are the opposite one. Okay. Then okay, for arrows, I need to put how we represent. Okay, if I have this arrow, um, in A, then I have BA in A up. And this is a way of presenting the definition of duality in category theory. It is more complex, the concept, because we can work with the different kind of categories and have in all categories the opposite category. But another properties like functors, for example, are not changing in when we take the dual statement. Then this is some ideas that I was exploring, because here we have that if we want to use the concept of duality, we need to find first two dual categories. And I think that even is possible to find the opposite category to one category, because we can find or we can revert all the statements in a category to statements in none of the category. In fact, in category theory, it is presented a property that when we find a theorem in a category, then it is not necessary to show the to make a demonstration of this of the theorem in the opposite category. Then we can say that it is possible even to build a category in the opposite categories from any category that we want. When Professor Garrett present to us the idea of work with the concept of duality in Clifford algebras, I was I have the question that what is the opposite category in Clifford algebras? How can build the opposite category? Because we can define Clifford algebra, for example, defining it, for example, like the Professor Garrett used to do with the product table. And then this is a definition of Clifford algebra. But Professor start with I'm going to change color. Starts with a set of in a space of dimension n. Then he says that E I E J I think that we can simplify saying that I found the different kind of notations, but we can introduce a pair of products that is the Clifford product, and with the unit that is a I with one is AI. I think that is everything that we need to define the Clifford algebra. And then after he used the idea of the signature of in the algebra with the idea that I with a I equal one for some for example of P and I equal to -1 for I higher than P. And then how we can get here the opposite category. And then I remember that in the Dedekind book, he works with quadratic forms, Q forms that are of order polynomials of order 2. And then he works, for example, selecting a base. I'm going to use the letter U for representing this AU are scalars in the field, and then sorry, no, not yet the quadratic form, but only the representation of an element of I'm going to see this is X for example, and this is ANUN, and then he asked about the a complementary base, because he says that it is possible to write X in terms of a relation. I need to change here to B. B1, U1 plus until UP. Oh, sorry. BP, UP, and then he used here the a complementary base that is BP plus 1, and we are going to use this notation and until W Q. Oh, sorry. N minus P. WQ. Q is N minus P. Then the complementary bases are the next, because he pressed this in this way. One complementary base, for example, can be in this W1 is A1 1, U1, etc. AUN, UN, and this until WN. I am going to write for a complete base, but in W instead of U for the base. Then U N. I have there is some of the notation, and there is a mistake here because I need to interchange. Here, this is N1, and then now N UN. And then this is another WN alternative base for the system. But then we can build an edge of the space in terms of U's and W's, and we find those the representation of X in terms of part of U's or part of N, and then we can find representations that all the we select are independent of the W's that we select, for example, in this expression. We can say that the W is a complementary of the base in terms of the U elements. Then we speak here about complementary bases in the terms that we speak in Grassmann algebras about representation of one element in the graded algebra, because in the graded algebra we can use the I think that needs one more. We can express the and now is a quadratic form Q, and a quadratic form is a I'm going to use G Willett using two elements. No, I'm going to use U and B. That is G applying to the product because B to the field. I'm going to write, for example, are real numbers. Then this is definition of the quadratic, and then it can be established in terms of the products between the bases of U, and then we can find that those are part of different kinds of products, or maybe we can say in another way, we can express this in terms of one symmetric and anti-symmetric part of this. I think that here, and I have here in the in a presentation. Maybe I need to change to the other computer. Then I need to close the whiteboard for a moment.
Okay.
Sorry. Okay, here we have the definition of the Grassmann algebra. We have here a vector a vector space and its dual. And then we can define an algebra inside the graded algebra of vectors and graded algebra of forms, then we can define both of these. And then here is the definition of the algebra of vector forms that is have the same properties that the Clifford algebra. Then Clifford algebra is inside this algebra of multivectors. And then we have here two kind of products. I think that I don't put. Okay. I don't put the two kinds of. Sorry.
So when you in this algebra of multi-vector forms, do you have some quadratic form or some notion of metric?
Yes, in this algebra of multiforms, maybe I need another. I have another slides that is better presented. Is with more detail present this algebra, and maybe I need to switch to that presentation. Of course, these two algebras comes from the quadratic form, exact. But sorry, I'm going to put this. Okay. Okay, I found here. I copied it. It was the presentation used in the memorial of Osievik conference. And then I'm going to put here. Okay, this is from the book of Young of um, okay, this is the same, but I wanted to relate. Okay, here there are the two parts of the product of B. Here denoted by U dot B, and is from the symmetric part of the tensor product of this vector space without the without the ideal wielded from the difference of the antisymmetric part. Then we get the product without the antisymmetric parts of products that and the Grassmann product. This is for a product of vectors and obtained in this way. Then we have okay, those are examples of vector forms. And here we have the definition for the exterior algebra of differential forms. And in the same way, we define the product, and here we have the quadratic forms related. We have here the product without the symmetric part. I have not a similar definition here, sorry, but is the to the definition that we find here. But now we need to define this in terms of the tensor product without the ideal of the symmetric parts. Then I need for those put here a plus sign because this is the symmetric part. Okay. Sorry, here is the definition below. Mm-hmm.
Yes.
Okay. Then we have, sorry?
Yes, I see.
Oh, okay. Okay. Then we have these two parts. We will these products for the vector forms and for the differential forms or scalar forms. Then those are the properties based in that definition. And the idea that in vector form, we have two kinds of products, the dot product, or maybe it's better to say the contraction product, because not even the dot product is a good definition for that, and the Grassmann product. And in the differential, we only have the Grassmann product, only that. Then those are the two forms that we are going to use, and those are important because we can using the Cartan lemma a relation between these two forms, vector forms and scalar forms, that have here defined the a product that is the evaluation, and this evaluation gives to us to an element of the scalars. Then with this, we have a complete description of the space. And it is needed both the expressions in the way that, both definitions, sorry, in the way that we can work with the duality concept. I don't know how in the in Clifford algebra, what is the definition of the opposite category in the way write this duality. I think that it is better to think there in terms of the complementary bases that Dedekind used before. And then with this definition, we can find the concept of duality there, and work with this idea. But I think that for the that if we want to go more inside this um, um, these ideas, we need both products, vector forms and scalar forms. We need to consider both space, vectors and scalar forms. Okay, this is some of the ideas that I was exploring, but I don't get organized results yet.
I like your comments at the beginning about the duality related to interchanging objects and arrows, and I wonder, that was your comment in relation to a Fano plane, and I'm not sure I understand completely what is the implication of a category in which the objects and maybe of a functor, I suppose, a functor that maps a category into its or maybe it's better to think of a functor category, right? So where the arrows are functors, and I'm struggling to think, how does one formalize this notion in category theory? In graph theory, it seems clear, right, that we can define a dual of a graph by interchanging the objects and arrows. But if we apply that graph duality to category theory, this is different than the category called dual that you defined, for example, of opposite category. So, and I don't understand yet what this category is if we exchange the objects and arrows. Is this well defined as a category, I suppose? That was my question. How can we define, for example, composition? How can we define composition in this category if we exchange the objects and the arrows? It seems intuitively that this is somehow related to the Fano plane concept, but I'm not sure. In order that the category with the object and arrows interchanged to still be a category, then I think we need certain axioms to be true. Certain things must be true about the category before it's even possible to define the dual category in that sense. but I'm not familiar with that part of category theory, I think. Did you have any comments?
But I think that yes, I think that your idea of uh, the question of what is the meaning of composition there, because in terms of vertices and arrows, we only adding arrows to the vertex, and not either because we need to explore that two arrows can be substituted, but one an arrow, and this is the idea of composition. But in terms of I don't. I remember that composition is in terms of grafting. If we can use grafting, then we are composing to two dots that are here representing the arrows. Then I think that we can for these relations, how the composition in one is reflected in the other one. But for example, there the grafting go from up to down, top to down, and it's the same that is, for example, with the arrows from left to right. Then it is not there are no change of the order in the composition, like is in the opposite categories. Then I cannot say that an commutative diagram is the opposite of an operath, because it's the same representation. The same order. Then I think that there we don't get opposite categories. Maybe if we think in terms of functors, then the functors is covariant, going from commutative diagrams to operas, or going from the representation of vertices and arrows to arrows and vertex, for example. Is the composition is covariant.
I see.
Then, okay, we need to think more about.
Yes. Okay, Brian, did you have any comments or questions for Dr. Cruz?
Well, actually, I think for me, the most like fundamental question would be what kind of duality is the fundamental one? For example, for me, at least, I have seen like a lot of cases where duality comes into play. And for me, the real question is where is like the basic like duality fundamental concept where all of the at least of my on my perspective, like the derivations of other kinds of duality or how it's represented. That could be for me the most important question, like which is the fundamental part of duality that we can like understand, and from that we can like approach or arrive to other representations.
Yeah. With your question, I remember the idea of duality in the theory of circuits, for example, where we can interchange dots and not and net and how do you say it? We can in a circuit all the how do you say it, Maya
Creo que es grid.
Grid. How do you change in the grid in the network but the grid I don't sure, but then the idea can interchange in a circuit the plate of currents with voltage, for example. We can interchange those, and it could be interesting to explore this with the duality theory, because, for example, voltage is a scalar form, and currents can be related with flux that are vectors forms.
Yeah.
Then I think that
sorry. And for me was like when I was thinking about it, like I only came with the conclusion that maybe comes from the conservation of energy, maybe, because when you think about it from a physical standpoint, because you need to, in order to do something, you need to give up something. It's not like you are going to create new things without losing something. So for me, at least, how I'm thinking about duality is like always when you try to implement something, even in mathematical structures, you need to consider like the opposite case to make like you are not creating something from nothing. You are only like changing the perspective. That's for me maybe the way I think duality could like comes from, maybe. I don't know.
But the idea is that we can start with a formal duality, and category theory give to us this formal definition. this is not necessarily related with opposite things. And I think that it is better expressed in the idea of adjoints. And then the concept of adjoints is used in this in this representation. For example, if we think that in terms of circuit theory, we can think that the current conservations is an expression of one adjoint concept that is the energy conservation. And I think that in terms of electromagnetics, current charge conservation is one law of fundamental law of electromagnetics that is parallel to the law of conservative field, electromagnetic field. Then we think that both laws are like adjoint concepts that are related in a way that both of them that are used in the interaction concept, and one is the adjoint of the other. Then I think that we can think the idea in these terms, but even in terms of category theory, because it could be better work
So
in a more precise way.
You propose then, I guess, that the fundamental duality that Brian suggested, the fundamental duality is the duality associated with an adjunction of some sort. So we must.
So
then.
So it could be like, for me to understand like that adjoint point of view, it could be like reversing a process. So, for example, if a process is going up, the adjoint would be the same process but going down, kind of.
No, not the same. No. Because those are different concepts. One is necessary to the other one in the way that both exist. Then one concept requires the other one.
Okay. And how could be like the adjoint of a process could be defined, if to understand your point of view, Professor?
For example, I prefer to think this in terms of and we can think in in all the physical fields, we can find a law related with property of matters and one law related with the interaction field. And those are a joint concept.
Yep, because I remember from category theory, there is a way to understand as objects on the category as morphisms, and also the other way around to understand like interchange what you said at first, arrows with points and points with arrows. I understand there is a way to do it in category theory, but for me, at least what I was like thinking about duality when I started to research that topic wasn't quite that representation. For me, was like how the morphisms inside of a category could be um, reversed to be complementary between each other. I don't know if I explained myself correctly, but for me, it wasn't like to interchange the objects of the category to morphisms or vice versa. It was more that changing the morphisms in one direction to another direction, or the objects um, with the objects staying as a like a reference point. And if we change the perspective of an object as a morphisms, we could change again like the direction.
I think that not is in this way, but I think that Professor Page want to say something. Do you want?
I'm not sure. I think it's sufficient for me to at this point to understand that the notion of adjunctions introduce the notion of duality, so that we have a pair of functors that are related by the adjunction, and perhaps it's the case that every time we have dual notions, at another level we have this notion of an adjunction. So every adjunction gives rise to a notion of duality, like through the functor and its opposite that is part of the adjunction. And this so in Brian's example, like where we have processes are normally the nodes in a or the vertices in a diagram. We do have an adjunction, I think, between a diagram in which we have interchanged the processes with the inputs and outputs of that process. So it's a more abstract version of the duality that we see in, for example, linear algebra between the vector space and its dual. So that, in a sense, the processes become the data, and that the input-output relationships become the process. Like it's so but this is shown again when we introduce, say, a category that has the notion of evaluation, and that we can relate in Grassmann algebra when we have, as you did when you said, for example, that we can think of Clifford algebra as embedded in Grassmann algebra. We can do this in the sense that we need to have this notion of evaluation, and evaluation implies some notion of an operation, of a process. Maybe the notion of a junction could be said to introduce a kind of abstract notion of evaluation in that sense. But all of this is searching for a kind of explanation, I think, for the structure that Dr. Sobczak was implying, right? That there is a notion of duality that goes beyond, or the notion of a linear vector space and its dual. Like so there's, and it seems that he would want to build Clifford algebra in a different way. So he's arguing, I think, in his papers that the Grassmann algebra, at least in his case of local duality, that there's a single Grassmann algebra that satisfies certain conditions. Then if that Grassmann algebra satisfies those conditions, then it can be used to define Clifford algebra. This still seems controversial to me. I still not sure. I mean, although I understand the derivations in his papers, I don't quite see the generality. So he gives some examples where this is true, but the claim that it's true in general for all Clifford algebras seem still uncertain. And so like you, I would wish to have a deeper foundation, a deeper algebraic foundation that goes maybe to category theory, maybe to the notion of adjunctions, which somehow it could be used to formalize the requirements on the Grassmann algebra that allow it to serve as a basis for this construction in a more general way. I'm not sure. So at this point, I remain uncertain. But
yeah, well, what I understand about the approach that Professor Sobchik, is the pronunciation correct? I don't know because in Spanish it is okay. Okay, is that when I came across with process theory and more specific CX diagrams, which is like a kind of derivation of process theories applied to quantum computing, they came across with the same idea, kind of the ones that Professor Sobchik is arriving and is also researching about. Is that in our case is called a strong complementarity, and it's come from a physical perspective when you have like two bases that are completely opposite to each other, and it only happens with a particular sets of bases. It doesn't happen for all of them. So that's where I like kind of relate that idea to what I understand about the CX diagrams. In that cases, what I think about that kind of global duality or local duality, for me, the global one is something that it's may could be like like something that you must consider when you are dealing with the generation of structures. It could be like algebraic structures or other kind of ones. For example, in my case, you consider it because when you are developing an algorithm and you want to do something in one of these two bases that have a global um, duality, or so sorry. And it has like a meaning that you are playing between these two bases, and you cannot like have information of both of them at the same time. But this comes from the theory of quantum mechanics, and I don't know if in a certain point that like kind of concept or principle is like introducing itself in the theory that Professor Subject is like developing. I don't know. I have also like a lot of questions about it, but for me, at least what I try to understand from my point of view is like something that it has like completely opposite poles, and you are trying to make them interact, and it cannot be possible for certain kind of structures. It could be algebraic structures, or in my case, bases. You cannot make them like interact because they are completely opposite. Maybe for certain kind of bases you can do it, but for particular set of bases you cannot. So for me, at least, that's my way of thinking about it.
Okay.
I like to add only a comment that I think that the definition of category theory for um, for duality is too formal and precise. Then I think that we can start with this definition, and is used for building a new category from any category that we want. Then we need to understand only the relations between the objects in the category, and then we can build the opposite category from this. The idea of adjunctions is more complex because either is a relation between two categories. And we need functors, and then we need to speak about the two kinds of functors that are covariant and contravariant functors, and then the concept of adjunction is wielded with this. Then I think the definition are with the high precision in terms of category theory. we need to explore more the, those the definitions and then try to apply it to Clifford algebra in the way of understand better how is this kind of category.
I recall that there's a connection with the operas that Dr. Shevich was very interested in this notion of operas, but some critical parts of this are related to the kind of thing that Bob Koch talks about in his papers on quantum mechanics, where we need to introduce the notion of color, right? So that we have, in addition to input and output, we need to have introduce the color of the input, right? So this is a type of diagram in which the edges in the diagram are of two different colors, and this gives rise to a kind of duality of interchanging the colors, which is related to the notion of defining a category in which we interchange the objects and the arrows. So it's, in other words, it's not enough to have a single type of duality. We need to have two kinds of dualities where we so with the language that includes these different colors, then we may, for example, have a process which has an input of one color and an input of another color, two different colors. So this process, which takes say one color which represents a function, for example, like a linear operator of some sort, and then the other color is the data for that operator. So then we can have an abstract process that represents evaluation, for example. So then with these two kinds of dualities, then in a single category, we can incorporate maybe it's good to think of them as adjunctions in the sense of endofunctors, so that in the single category we have an endofunctor that maps the category back into itself. But for every such endofunctor, we have an opposite endofunctor defined by an adjunction. That kind of structure is what I thought perhaps is similar to what Dr. Sobczak is doing. But I don't see that kind of structure clearly defined in his current papers. And so I'm on that. So I'm struggling to say, well, how can we have this notion of local duality? I'm not sure that there is enough structure, enough structure in Grassmann algebra itself, or in the axioms that he currently is using in his papers to fully generalize his construction, right? That he has only enough structure to give the examples that he's using so far, but the general construction still seems unclear to me. I hope that maybe in 3 weeks' time or in some future meeting, Dr. Sobchak will fill in more details, and provide more of what he sees as the ultimate relationship between this global duality and local duality. It's still, for me, it's still a question mark. I don't know.
Okay. Yes.
Okay.
Same for me. Yeah.
I think we will plan to meet in 3 weeks' time again, if that's okay. I think I'll ask Dr. Sobchak if he would be prepared to make a presentation at that time in 3 weeks. If he, I know he might, I'm not sure of his schedule in Mexico, and he did say that he had some difficulty with communication with network bandwidth where he was located was not sufficient for Zoom. But on the other hand, in 3 weeks' time, he may no longer be in Mexico, so I'm not sure of his plans.
Yes, I think that the problem is because he now in Puebla have not a good connection to internet, but I think that he go back to North Carolina the next week. Then
yes,
I
okay.
think I hope we Mhm.
Okay, well, so let's plan to meet in 3 weeks, and I will confirm with Dr. Sobchak if he can make a presentation for us at that time.
Yeah, I think
Okay.
we could manage that, and also like focus on those 2 points, the global duality and the local duality, to kind of grasp. And also if you can like get local duality from global duality or vice versa, I don't know, but I am thinking that maybe global duality, you with some operations you can arrive to the local duality. That also, it's like a remaining question for me, if they are related to each other in a certain way. So okay.
All right. So let's say that's our meeting for this week, this time, and we'll see you in 3 weeks' time. Yeah.
See you. Bye bye.
Bye bye.